Hello everyone, Mr. Fawcett here, and we're back with another AP Calculus lesson. Today we're going to continue our discussion of how to use integrals to find volume. But the solids that we create today and the solids that we're going to calculate the volume of, we're going to form them in a different way than we formed our solids previously. Previously we've raised cross sections out of a two-dimensional space to create a solid, right? We've used squares, rectangles, semicircles, and a couple different types of triangles. Well, today we're going to start a discussion of what happens when we revolve a two-dimensional shape, right? So a two-dimensional region, and we revolve it around an axis, and that's going to create a three-dimensional solid. And then we're going to look at how to calculate these solids. And you're going to see that we're still going to use the idea of cross sections, an infinite amount of them, and then using integrals to sum all of their volumes. So let's look at our introduction problem, and we'll jump right in. It says, let R be the region enclosed by the x-axis, the line x equals 1, the line x equals 3, and the curve y is equal to 1 over x. It says a solid is generated by rotating R around the x-axis. We want to find the volume of that solid. We'll give an exact answer in terms of pi. That just means we're going to be doing this by hand. We're not going to be using a calculator. Okay, let's start by trying to visualize what's going on here. They're rotating this region R around the x-axis. So let me first just highlight our x-axis so we get that to pop out a little bit more. Okay. Now, when we're revolving this region, it means we're going to take a point on the curve, and we're going to rotate this point. Oops. There's a point. We're going to rotate it 360 degrees around the x-axis, just like that. We're then going to take another point. We're going to rotate it 360 degrees around the x-axis. It wasn't the best. Generally, when you're drawing a 3D diagram, if that curve is going to be behind your solid, you do it using a dashed curve. That's why this is dashed right here. And I just kind of skipped ahead here, but essentially we're going to have a bunch of these little discs. Right? And together, those are going to form this little tube-shaped figure that sort of trails off there at the top. So this would be our three-dimensional solid made up of these little discs. Let me turn this around for you. So let's just rotate the plane here. So I just rotated it 90 degrees in the counterclockwise direction just to show you another perspective of it. We need to now go ahead and try to find the volume of the solid. And the idea is the same as it has been the last couple of lessons. Can we write out a formula for the volume of one of these little cross sections, right? So the red, the pink, the orange, or the blue. And let me just sketch in, give this cross section a little depth here. Right, so we're actually looking at a small little disc, right, rather than just a little slice. So up here, same thing. Not sure how good that is, but anyway, the idea is not only is it a circle, it's going to be a circle with a little bit of a depth. So can we write a volume equation for essentially a cylinder, right? A cylinder with an infinitely small depth, right? Our depth is going to be what we call that infinitesimal, that dx. Well, we should know what the volume of a cylinder is. Color coordinate this again. So the volume of the red disk. Volume of a cylinder is just pi r squared times h, so the area of a circle times the height or the distance between the bases. Well, what is our radius and what is our height here? Well, the radius, if we go over here and look at this left example, the radius is going to be the distance between the curve and the x-axis. And that's just going to be our y value of our function. So that's going to be 1 over, well, let's keep our pi, and then we have 1 over x. We're going to be squaring it. So again, here the radius is just the distance between the function and the x-axis, which means it's going to be the y value of the function. The height, right, the infinitely small height or the width of these disks, well, that's going to be our dx, right, our infinitesimal. Because we want as many of these disks as we can so that when we calculate the volume, it's the actual volume. To sum up all of these volumes of all of these individual disks, well, I'm just going to take the integral. So let's jump down here. The volume of the whole solid. So the integral, let's remember our boundaries here. I kind of covered them up as I was drawing, but we're going from 1 on the x-axis all the way up to 3. So the integral on the interval 1 to 3 of the volume of the disks. So pi times 1 over x squared dx. And we could go ahead and evaluate that by hand, actually, which we will do. But again, the idea is, where does this integral come from? How did we set this up? Well, we came up with a solid using a new method, right? This is called a solid of revolution. But then we were still finding the volume of a single cross-section, coming up with the volume formula for a single cross-section, and then just integrating over the interval. Okay, let's go ahead and evaluate this by hand. Let's see if I can do this up here on the top left, see if I have enough room. We can actually pull the pi out. It's up to you. You can keep the pi inside your integral. You can pull it out because it is a constant. I am going to square 1 over x. So I'm going to get 1 over x squared dx. If I take my antiderivative, well, that's going to give me negative 1 over x to the first. You could think of, and actually, we should just make sure that we're multiplying there. You could think about that using the reverse power rule. Right, 1 over x squared is really x to the power of negative 2. Right, so reverse power rule, we're actually going to add 1 to the exponent. So x to the power of negative 1 and divide by the new exponent. So divide by negative 1. These two are not equal to each other because I'm taking the antiderivative. But this would be equal to negative 1 over x. Okay, let's keep going though. Need to evaluate this from 1 to 3. So it's going to give me pi times negative 1 over 3 minus negative 1 over 1. So I get negative 1/3 plus 1. That gives me 2/3. So I get 2/3 times pi. That should be the volume of this solid. Okay, we are going to do 2 more examples, I believe. Let's clear this. We have something to fill in at the bottom here. This is kind of what we talked about. When finding the volume of a solid of revolution, your goal is to find the volume of a single slice and then integrate over the the given boundaries. So again, same idea that we've been doing for these last couple of lessons. This time we're just creating our solid in a different way, solid of revolution. Okay, we're going to jump down here to this one right here. It says let R be the region enclosed by the positive x-axis, the positive y-axis, and the curve y equals the square root of the difference of 9 and x squared. We're rotating this around the x-axis, so again our integral is going to be in terms of x. We want to find the volume of the solid, give an exact answer in terms of pi. Well, I think we understand, or maybe we start to have an idea of what this solid is going to look like. Right? I'm going to take a point on the curve, and I'm going to rotate it around the x-axis. Come back up. There's one of my disks. There's another one. We'll do 2 more. Although my last one will have no area or volume. This last one up here, right, that circle or cylinder with an infinitely small depth is going to have no area or volume, right, because it's just a point. And if I revolve a point that's on the axis around the x-axis, it's just going to stay where it's at. So our shape is going to look, whoops, wasn't very good, was it? So our shape is going to be this dome. Man, really not good. Should have just paused the video. That's a little better. Our shape is going to be this dome-like figure, maybe a little bit like an igloo. Something like that. If I rotated it, it would look something like that. There's my cross sections. Okay, so our cross sections are going to all be the same here, right? They're still circles or cylinders with an infinitely small depth. So I'm going to be working with the same formula, right? The volume of one of these is going to be equal to pi r squared times h. Our radius here, again, is just the distance between the function and the x-axis. So it's going to be equal to the y value of the function. So the square root of 9 minus x squared. And I get to square that. My height is just going to be my dx. So that's the volume of 1. I want to sum all of these disks up, right? So the volume of the whole solid is going to be equal to the integral. We're going from 0 to this x value right here. But notice it doesn't give me that. So here in this problem, I have an extra step. I've got to go ahead and find that upper limit of integration. Pause the video, think about how you would do that. How am I going to find that upper limit of integration? Well, I just need to set the function equal to 0, right? Because that upper limit of integration is a 0 of the function in the positive or the first quadrant. So 0 equals the square root of 9 minus x squared. Square both sides. 0 is equal to 9 minus x squared. X squared is equal to 9. X is equal to positive or negative 3. I'm looking in the first quadrant, though, so I am looking at x equals 3. So my upper limit of integration, 3. Everything else will stay the same. You'll notice there is some simplifying we can do here. We'll do that in our next step. Before I integrate, I will simplify the square root and the square to make things a little easier. You can also pull your pi out of the integral. And this one's pretty straightforward to evaluate. Let's see if I can squeeze it in here. Antiderivative would be 9x minus 1/3 x cubed, evaluating from 0 to 3. This is going to be tight. We get 27 minus, 27 minus 1/3 times 27. And of course, when I substitute in 0 to both of those terms, I'm going to get 0. We'll go up here. 27 minus 1/3 of 27, so 27 minus 9, that gives me 18. So 18 pi. 18 pi would be that volume. Okay, one more example. Notice that we've only been rotating around the x-axis so far. I do want to go over one example where you have to rotate around the y, just so we have practice setting up an integral in terms of y. So let's clear this. Let's jump down to this problem right here. Here we're just going to be setting up the integral, so we won't be evaluating. It says let R be the region enclosed by the y-axis, the line y equals 2, and the line y equals 5, and the curve y equals e to the x. This solid is generated by rotating R around the y-axis, and we need to find out which of these integrals would give the volume of the solid. Well, let's give a little visual. Taking a point, going to rotate it 360 degrees around. Again, we're going to get a little, I was going to say a dome figure, but it's not going to quite be a dome because our bottom's cut off. But we're going to get a figure that looks like this. As always, we are getting a slice that is a little mini cylinder, right, with an infinitely small depth. So the volume of one of these slices is going to be pi r squared times h. Well, the radius this time is the distance between the function or the curve and the y-axis. So we want our function to be in terms of y, not x. Well, we need to take our function. We need to rewrite it in terms of y. So we need to get the x by itself. Well, to undo our natural exponential function, we're going to take the natural log. So take the natural log of both sides. That will simplify my e. So I will get the natural log of y is equal to x. Well, that means that my radius value is going to be the natural log of y. So I will square that. My height, well, my infinitely thin disks, the depth is going to be a very small change in y, right? So it's going to be a dy rather than a dx. Okay, that is the volume of one of these disks. I need to set up the integral for the volume of all of the disks combined, or the volume of the whole solid. So I need to set up an integral. Well, I'm going from 2 to 5 on the y-axis, and my limits of integration need to be in terms of y, right? Because my disks are perpendicular to the y-axis. We're revolving around the y-axis. So limits of integration need to be in terms of y. My function needs to be in terms of y. That's why we converted, etc. So I get pi. Here's another way to write the natural log of y squared. Actually, I'll keep it the way I did. I was going to say you can write the natural log of y squared as this. It means the same thing, but since our answers look like the way I wrote it before, we'll keep it like that. You can also pull the pi outside of the integral, right? So final integral should look like this. And it looks like that matches one of the first two. It looks like it matches B. So again, just like before, where we could have our cross sections perpendicular, like our squares, our rectangles, our semicircles, our triangles, they could be perpendicular to either the x or the y axis. We can also revolve around either the x or the y axis. And depending on which axis you're revolving, that's going to be the variable that you want to set your integral up in terms of. Okay, that is going to do it for this video. As always, enjoy the rest of your day, and we will look forward to seeing you next time.